and welcome. Today, we're going to be looking at the unit test for modeling energy, one of our topics in physics, both honors and standard. As always, we're going to be going through all 9 of these questions in this unit test to make sure you understand how to approach and solve these questions. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our first question. Here we go. A student builds a track for his 0.060 kilogram toy car that includes a loop with a height of 0.4 meters. The car loses 0.16 joules of energy when it travels from its starting point to the top of the loop. The velocity of the toy car at the top of the loop is 1.4 meters per second. Use g equals 9.8 meters per second. Okay, let's see. Okay, so we're trying to find the initial height of the car. How are we going to do that? Well, how we can do that is we can do that by quantifying the amount of energy at the start, and at the end. Okay, so let's think about the end first because that seems simpler. So you have a loop with a height of 0.4 meters. Okay, so 0.4 meters times g, 9.8, times and math, 0.06, which is going to be 0.2352 joules. And then the velocity of the car at the top of the loop is 1.4 meters per second, 1.4 squared times 0.5 times the mass 0.06 is 0.0588 joules. And then I add that up to get 0.294 joules. All right. And the car loses 0.16 joules of energy when it travels from its starting point to the top of the loop. The velocity of the toy car at the top of the loop is 1.4 meters per second. Use g equals 9.8 meters per second, and we're trying to find the initial height. So what do we know about the start? So the start, let's see. So the start, so it loses 0.16 joules of energy from its starting point to the top. So we're going to take that 0.294 and add 0.16 joules. And we get 0.454. Okay, 0.454 joules. Now we don't know. We don't think it's moving because it's starting then, so it's not moving. The only type of energy it has is gravitational potential. So we take that 0.454, divide it by 9.8, divide it by the 0.06, and we get that it has a height of 0.77 meters. 0.77 meters. And if you're confused as to how this works and like why the starting point is higher than the loop, right? Like we don't need to know that, right? What I'm guessing happens is that like starts up here and then it goes down and then has a loop down here or something like I don't know, but there is no boundary on what can or can't be the initial height. And so that is our answer. And we can keep going to the next question. Rudra pours hot tea into a cup for his breakfast and places a cup on the kitchen. Which of the following would describe possible ways heat would be transferred in this system? Okay, so hot tea in the cup, right? So the tea is hot. Right? Tea's hot. Tea. So we can just make a list. Hot, cold, or just not hot. So hot is tea. Everything else is cold. So everything else. That's essentially it. All right, so we're going to transfer stuff from the tea to other stuff. So heat transfers from the tea to the china cup. Right, china cup is colder than the tea, so the heat transfers from the tea to the china cup. That's always how it works. Stuff with more heat transfers stuff with less heat to make it equilibrium, to make it equal, to go into equilibrium. Heat transfers from the tea to the air. Tea is hotter than the air, so transfers to the air. Then we have our other two heat transfers from the air to the china cup and heat transfers from the china cup to the air. Okay, let's see. So which way would it go? Which is hotter, the air or the china cup? Right, we have to think about which one is hotter. Right, if the heat is transferring from the tea to the air, heat is transferring from the tea to the china cup. but we need to choose another answer, and we need to know if the heat is going to transfer from the air to the China cup or from the China cup to the air. Which one is hotter? That's the one that's going to be doing the transferring, that's going to be losing the heat. So the air is going to be room temperature, right? The hot tea is obviously a lot hotter than the room temperature. And for the cup, well, you're pouring the hot tea in that, so more heat is going to flow in the cup, in the China cup, I think. So heat is going to transfer from that China cup to the air. And that's our answer. And we can move on to the next question. Let's keep going. 64-kilogram snowboarder launches off a ramp. At the top of his jump, he is 3.1 meters above the ground and has a speed of 21 meters per second. Use G equals 9.8 meters per second. Calculate the mechanical energy of the snowboarder. Round your answer to the nearest thousand. Okay. Calculating the mechanical energy of the snowboarder. So we have kinetic energy, which is 1/2 mv squared. So 0.5 times the mass, 64, times the velocity, 21 squared. That gives us 14,112 joules. And then we have the gravitational potential, which is going to be mass, 64, times gravity, 9.8, times the height, 3.1. That's 1944 joules. So we add that up, 16,056.32 joules. Round to the nearest thousand, that's going to be 16,000 joules. And we can keep going to the next question. We are trying to find the amount of heat transferred between two substances. In order to do this, you plan to place both substances in a thermally isolated container and wait until the system reaches thermal equilibrium. You need to decide what measurements you need to take. Remember that heat transfer is described by the equation Q equals mc delta T, where m is the mass, c is the specific heat, and delta T is the change in temperature. Assume you are able to look up the specific heat capacities of both substances. Which of the following sets of measurements would best allow you to determine the heat transfer between the two substances? So we have A, the initial mass of the two substances and the final temperature of the system. B, the total volume of the two substances and the final temperature of the system. The initial mass of the temperature of one of the substances and the final temperature of the system. Okay, let's see. Let's see. Well, what do we have? We have, well, for answer choice B, we have the volume of the two substances and the final temperature of the system. Volume doesn't play any part in this because we don't have a density, so we can't calculate mass. And mass is where everything's at. So using the volume doesn't do anything, so B has to be incorrect. Alright, then our other answer choices are A and C. Right, A says the initial mass of both substances and the final temperature of the system. C says the initial mass and temperature of one of the substances and the final temperature of the system. Let's look at what information we get from each of these. So from A, initial mass of the two substances and the final temperature of the system. So you'd have two masses and you'd have a final temperature. But you couldn't find a change in temperature because you wouldn't know where you started. So that's kind of questionable. And C, the initial mass and temperature of one of the substances and the final temperature of the system, well, you would know the change in temperature for that one mass. You know the specific heat capacity and then the mass of that. Mass, specific heat capacity, and change in temperature, you could find the heat transfer. And it's going to be the same both ways, just in like one's going to be positive, one's going to be negative. So that would help you find the heat transfer with just that information. So that's our answer. Let's keep going. Kevin uses an elevator to lift 10 boxes of 10 kilograms each up to the fourth floor at a height of 18 meters. When he's finished, Kevin notices that the elevator motor and brakes as well as the air around them are hot. So that's going to be thermal energy, right? If it's hot, thermal energy. So we're going to assume, let's see what we see. Let's see what we get here. Device connected to the elevator indicates that 24,100 joules of energy were consumed. Use G equals 9.8 meters per second. Okay, so we see these answer choices. And let's figure out, first of all, how much energy they actually used for the actual purpose, which is lifting the boxes, lifting everything up. Okay, so 10 boxes, 10 kilograms each, so 100 kilograms, fourth floor, 18 meters. So 18 is the height, times 9.8, times 9.8. That's going to be 17,640 gravitational potential energy. Okay. So the box received that much gravitational potential energy. Well, that is true, right? The boxes did receive that much gravitational potential energy. Now, 24,100 minus that is going to give you 6,460 joules. Now, the boxes did not receive that much. They received that much. And nothing else is receiving this much because the elevator isn't receiving anything, it's using stuff. The motor and brakes would have received, transformed the rest of that energy into heat, and that's why everything's hot. That's 6,460 joules. That is going to be the heat. That's going to make the brakes and all that stuff hot. That's why it's hot. Let's keep going. Group of students are having fun in the school gym. One of them rolls a 0.05 kilogram beach ball across the floor at a speed of 1.0 meters per second. Another student kicks a 0.55 dodgeball to follow the beach ball at a speed of 2.5 meters per second. Both balls roll until they eventually collide. After the collision, the beach ball is moving at 3.75 meters per second, and the dodgeball is moving at 2.25 meters per second. Assume there is no friction. Okay. So here's what we're gonna do. We're gonna make what we call this table to demonstrate, to model what's going on. All right. So we have a start, we have a finish, and on the first row, this first row here is going to be for the beach ball. The second row is going to be for the dodgeball. All right. So the beach ball 0.05 times 1 squared over 2. 0.025. That's how much kinetic energy the beach ball has. And the dodgeball is going to be 0.55 times 2.5 squared over 2, or 1.71875. I know the number of significant figures is probably too much, but we don't really care about that until the end. Right, beach ball is moving at 3.75 meters per second, so that's going to be 0.05 times 3.75 squared over 2. So that is going to be 0.351. 3515625. Yeah. So dot dot dot. And then for the bottom, you have 2.25 squared times the 0.55 over the 2, 1.39. 2, on and on. Dot dot dot. So I'm going to add the energy at the end, and I get 1.74375. I'm going to add the energy at the beginning, and I'm going to get 1.74375. All right, so this is a perfectly elastic collision. The energy went from one thing and it went to the other thing. Everything is good, right? The energy is the system doesn't lose any energy. It has the same energy as it started with, same energy. All right, the exact same amount of energy at the beginning and the end. What did change is that, let's see. So the beach ball gained some energy, around 0.33 joules of energy, and this one lost 0.33 joules of energy. So the beach ball got 0.33 joules. The dodgeball lost 0.33 joules. So the dodgeball transfers 0.33 joules of energy to the beach ball. So our answer is D. And we can keep going to the next question. People get into a roller coaster at the beginning of the track, which is high above the ground. When the car is released and rolls downhill, it increases in speed. When the car rolls uphill on the second hill in the ride, it decreases in speed. Why must each hill in the ride be smaller than the previous hill? Let's see. So, if you think about this from a purely, if you think about it just from a purely energy perspective, right? If you're looking at it like this, and the heights are going to be the same, if you start like right here, then by the time you get here, it's gonna stop. Okay? What does that mean? What do we mean? What does that mean? Why do we care? Well, what it means is that if you start here and you go down and you come back up, you have to go lower, so it still has speed when it gets there, and it can go back down. All right, that's the first thing. The second thing is that you're losing energy due to friction. Friction exists in everything. Air friction. There's the friction between the friction between like the wheels on the bottom of the car and the ramp or the track or whatever. You're gonna lose energy to friction. You always lose energy to friction, unless they tell you friction is negligible. Unless they tell you friction is negligible. Otherwise, friction, it happens. You lose energy. So you're going to need to make the hills smaller and smaller and smaller, so that the amount of energy that the car has left, is enough to get over those hills. That's why the hill in each ride must be smaller than the previous hill, because it loses some energy due to friction. All right, so that is our answer, and we can keep going to the next question. A student building a game wants to launch a 0.0060 kilogram marble at 11 meters per second using a spring. The spring constant is 380 newtons per meter. Assume no mechanical energy is lost from the system. So we're going to use um, our formula for getting the kinetic energy, 0.006 times 11 squared over 2, 0.363. 0.363 joules. Right, 0.0363 joules. And then we need to think about what is the formula for the energy of a spring, and it's going to be 1/2 kx squared, where k is the spring constant, 380, and x is the distance. So you have 1/2 0.5 times 380 is going to be 190 times x squared equals 0.363. So 0.363 divided by 190, take the square root of that, and you get that the spring is going to have to be compressed 0.044 meters to the nearest thousand. That's how much you have to compress it. Let's keep going. The suspension system of a car contains springs that are compressed to absorb energy. One of the car's springs, with a spring constant of 85,000 newtons per meter, is compressed 0.019 meters as the car moves up and down on a bumpy road. Calculate the elastic potential energy of the compressed car spring. Remember, it's 1/2 kx squared. So 1/2 times 85,000 times 0.019 squared. And the nearest integer, that is 15 joules. And we are done. Alright, so that was this unit test on modeling energy. I hope you learned something from this video, or I hope you found it informative. Be sure to stay tuned for next time when we continue looking at more physics topics in this physics course. I'll see you then.